castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
So, good morning everyone. My name is Martin Halaj and I'm from Comenius University in Bratislava, and today I will be talking about automatic mesh generation for realistic human avatars. So first I want to start with a short intro into SMPL model and what it is. It is a realistic 3D model of a human body. For us it is important that it is parametric model, so we can construct it from various sets of parameters, and the most important parameters for us will be shape parameters, because these directly influence the physical shape of the avatar, like height or circumferences of various body parts. So here you can see the visualization of SMPL model with a highlighted armature and joints. Our motivation was to give users a way to create virtual copies of themselves. Our solution is based on creating avatars from anthropometric measurements. The first approach was to develop a pipeline where user can insert the measurements he measured himself, and we can create avatar. However, we realized that manual measuring can be time consuming, so we added a new part of the pipeline for extracting the body measurements directly from the photo. So user can take a photo, we extract body measurements, which we convert to SMPL shape parameters, from which we can create a SMPL model on which we then apply skin texture and generate a simple clothes. So the whole presentation is divided into a few parts, where each part is covering different part of the proposed pipeline. So we started data generation. Body M dataset is one of a few datasets that captures human bodies of real people. They captured over 2,000 subjects. And for each subject, there are 14 different measurements. The problem is that in the work, they do not define how precisely they took these measurements, so it's causing little inaccuracy. Here you can see the example of the dataset. On the left, you can see the real photos they captured. However, due to privacy protection of the participants, they only publish the silhouette ones you can see next to them. To generate synthetic data, we used a data generator called Suract. Originally, it was used to generate synthetic videos for action recognition tasks. Experiments in their work show that using synthetic data in combination with real data can improve the performance of neural network. So we decided to extend body M dataset and adjust Suract's framework to our needs. So here you can see the example of dataset we generated. We generated over 1 million files for 100,000 virtual subjects. Here you can see the one sample for one avatar, which consists from front and side view of the avatar, with and without background, mesh of the avatar, and also position of joints in 3D space. So in this section, we look on evaluation of this synthetic data. We measured the avatars I mentioned previously, and we found 10 common measurements between body M dataset and our synthetic data. So here is the architecture of our network. As an input, we have 2 silhouette photos, which we put into ResNet 18 blocks, and we concatenate the output. We have few dense layers or fully connected layers, and the output what is 10 measurements. Here you can see the test results of our network. The network, which was trained using the combination of synthetic and real data, has a significantly smaller mean absolute error in centimeters than the network trained only using real data. And the same applies to precision. Now, when we have user measurements extracted, we need to convert them to SMPL parameters in order to create a 3D model. So we used SMPL anthropometry tool developed by David Branich to generate a training dataset. We generated a pairs of body measurements and expected shape parameters for SMPL model. We used this dataset to train various different models, but we achieved the best results with the polynomial regression of the second degree. We did 2 experiments. The first experiment, we select 5 basic measurements, which was height, chest circumference, inside leg height, shoulder breadth, and waist circumference. And in the second experiment, we use all available 16 parameters. Here you can see these 5 basic parameters visualized. And again, these are the test results for the first experiment. The most important value for us is in the middle, the mean absolute error in centimeters. You can see it is really small for both models. However, the biggest difference is the largest error, where you can see that the largest error of linear regression is much bigger than in case of polynomial regression. Here you can see the visualization of all 16 measurements, and again, the results. You can see the values are really small, the errors, but still we have significant difference in the largest error between these 2 models. So we already have the body model. So the last step is to give it some colors and clothes. We tried 2 different approaches to creating the clothes. The first method was to use sewing to create clothes. So we sewed 2 planes to create, for example, the shirt. However, with this method, we have the problems with scaling the clothes. And the second method we used was extruding mesh of the avatars. Here is the result of the first method, where you can see that due to the sewing, we have loosely sleeves. And here you can see avatars generating using the second method with applied skin texture and also with applied materials to clothes, with different types of shirts and also with trousers. The last tool we developed utilized the segmentation neural network self-correcting for human parsing. We use it to parse the human photo, as you can see, and we are able to extract from it the average color for the upper body clothes and the lower body clothes. Thank you for your attention.
Okay, thank you very much, Martin, for a nice presentation. So now it's time for your questions.
Thank you for the presentation. I have a question. You mentioned in one of the tables there the precision and some mean absolute error. So how is the precision defined in this scenario?
For precision, we defined the threshold of error 5 centimeters. If it was more, it was not good, and it was under, we qualified as a good.
I have a question. So have you considered maybe setting these different thresholds? Because I assume that, in the chest measurement, having 5 centimeters is not so significant as having it in your arm length or something, not arm length, but like some other diameter of the arm or something, where 5 centimeters could be quite significant. So maybe perhaps using some relative error would be better in this case, or mean relative error would be more meaningful in terms of and then you can express it in terms of some percentage or some relative error.
It is definitely something to think about. I have the table for each error for each part, but I didn't fit it into presentation. So, but yes, thank you for the idea.
So I have one question. If you have errors, so what works the best? Which part of the body is the easiest to estimate the measurement for?
I'm not quite sure, but I think the chest circumference, but I can't tell for sure.
Okay, thank you. Thanks.
Are there any other questions from the audience? If no, I have one. I have seen those 2 data sets before, and someone mentioned that they have problems with these binary masks, and sometimes they are incorrect and there are missing parts and things like that. So can you comment on this? So have you any problems during the training, the network, and how big is the part of the data set which has these incorrect masks?
When I look at the body data set, some pictures have some fragments, but it is really a small amount. So we decided to not simulate noise in the synthetic pictures because there was not much pictures with fragments in binary masks.
Okay, so you didn't like filter them out or anything, just the network deal with them?
No. Yes.
Okay, thank you very much. Are there maybe any other questions? But we are nicely on time, so we can thank the speaker again.
Swing to the beat where the pixels play, from rendering to VR. It's a pixel